Hi boys and girls, this is lecture 2.2 in Unit 2. The topic, finding limits numerically and graphically. We have briefly discussed the idea of a limit and its importance to calculus, but exactly what is a limit? A limit describes the behavior of a function at a particular point. More formally, if f of x, the function, becomes arbitrarily close to a single number L, as x approaches c from either side, the limit of f of x as x approaches c is L. Of course, this letter denotes the limit. This limit is written in this notation and can be read one of two ways. The limit as x approaches c of f of x equals L, or you could read it this way, the limit of f of x as x approaches c is L. In general, there are three approaches to use when evaluating limits: numerically, graphically, and analytically. In this lecture, we're going to study numerical and graphical methods for finding a limit. Let's take a look at our friendly function here. We have f of x is equal to x cubed minus 1 over x minus 1. Since this is a rational function, we have to examine the denominator and determine if any value should be excluded from the domain. As you can see, if x is equal to 1, that denominator becomes 0. Therefore, we must exclude 1 from the domain of this function. And when we graph this function, we would have to, if we were graphing it manually, we would have to put a little circle here at the x value 1 to indicate that the function actually isn't defined there. We would be finding y values for all of these other x values, no problem. But when x is equal to 1, we don't have a value. At least we don't get it from the function, because since the denominator is equal to 0 at 1, the function is undefined there. On your graphing calculator, you might not be able to see any little discrepancy here at x equals 1, but analytically we know it's there because we understand the behavior of rational functions. Now, let's take a moment to examine what the limit would be as x approaches 1 in this function. It's going to be a different matter than evaluating the function value. So as we go to the x-axis and begin to approach 1 from the left, what are the function values, the y values, doing? As you can see, as we get closer and closer to that target point here, that it looks as though the function would like to be a 3 there. Let's see if that's also true from the right. As you can see, as we move towards 1, our target value here on the x-axis, the function values, the y values, once again, from both sides, are approaching the number 3. So even though the function is not defined at 1 and will never be defined at 1 because it's a rational function, we do have a limit there. The behavior, remember this limit describes the behavior of the function. The behavior of the function is indicating that at 1, 3 should be the function value. Now let's look at the numerical data. On the x-axis, remember our target value is 1. What is happening in the y values when we're getting closer and closer to 1 in the x values? We'll notice from the left we have x values 0.75, 0.9, 0.99, 0.999. And what are the y values doing? 2.313, 2.710, 2.970, 2.997. Doesn't it look as though those numeric values are really trying to become a 3 there? How about from the right? As we come from the right on the x-axis, 1.25, 1.1, 1.01, 1.001, the y values become 3.813, 3.313, 3.310, 3.030, 3.003. You can see that they are getting closer and closer to the number 3. So even though, once again, there is no function value at 1, and there never will be, there is a limit there. The behavior of the function is indicating it would like to be a 3 at x equals 1. And that is how we determine graphically and numerically what a limit of a function is at a particular value. Now let's examine the numerical and graphical data of another function in order to determine a limit. Here is the function that we're going to look at. We have f of x is equal to x over the square root of x plus 1 minus 1. Once again, it's a rational function, therefore we need to examine the denominator in order to determine if there's anything that should be excluded from the domain. You can see that if x is equal to 0, we would have this situation. 0 plus 1 is 1, the square root of 1 is 1, minus 1 is 0. Letting x be 0 would make this denominator become 0, which is not allowed. So 0 is excluded from the domain of this function, and every other x value in this domain will produce a y value, a function value, but 0 won't. Therefore, once again, if we were manually graphing this function, we would need to put a little open circle here to indicate that at 0 we do not have a function value. So that leads us to this point. Although this function may be undefined at x equals 0, it is still possible that a limit exists at that point. Analyzing the numerical and graphical data surrounding the point in question allows us to determine the value of the limit. Now, because of the previous example, you may already have understood that what you must do is look at the behavior of the function around x equals 0. You can see what the function is trying to be there, and that is the limit. As you get closer and closer to 0 from the left and from the right, you can see that on the y values, we're getting closer and closer to the value 2. At x equals 0, the function is behaving as though 2 should be the y value. Once again, I have to point out that there is no function value there, and there never will be because of the configuration of this function. But there is a limit there. The function is behaving as though at 0, the function value should be 2, and that would be the limit of the function at 0. Now let's look at the numeric data just to verify what we can see on the graph. Once again, our target value on the x-axis is 0, and we're wondering, what is the function doing? What are the y values doing numerically around that place? From the left on the x-axis as we get closer and closer to 0, and from the right on the x-axis as we get closer and closer to 0, look at the function values. 1.99499, 1.99950, 1.99995. That really looks as though it would like to be a 2, doesn't it? From the right, 2.00499, 2.00050, 2.00005. Once again, numbers that are getting incredibly close to 2. So you can see that your numeric data and your graphical data verify the fact that at x equals 0, the limit of this function is 2. In the previous examples, we determined that the existence or non-existence of f of x at a given point has no bearing on whether the limit exists at that point. In those two examples, we had functioned where a point was undefined, but we found a limit to exist at that point regardless. We're going to see that in this example as well. Here we have a piecewise function, and it's arbitrarily defined in this way. When x is not 2, we want the function value to be 1. When x is 2, we want the function value to be 0. So that produces this graph. We have a horizontal line at 1 for every x value except for 2. Therefore, at 2, since it's defined to be something else, we have this open circle indicating that is not where the function value is for 2. Rather, here it is at 0. So what is the limit at x is equal to 2? We do have a function value here. Will the limit be the same as the function value? Notice that the function approaches 1 from both the left and the right as we approach x equals 2 from the left and the right. So as we're approaching x equals 2, from the left and the right, the function is approaching the value 1. So the function is indicating that it would like to be a 1 here when x is equal to 2. Unfortunately, the function is defined to be a different value. It doesn't matter that f of 2 is equal to 0. The function would clearly rather be 1 at that point. Thus, the limit of the function f of x as x approaches 2 is 1, even though the function value at 2 is 0. So here we have a case where we do have a function value at our target point. It's just that the behavior of the function is indicating it would rather be something different than the defined function value. So in this case, the function value f of 2 is 0, but the limit of this function as x approaches 2 is 1, something completely different. Now you might be wondering, is it always true that the function value is different from the limit at a specific point? No, not at all. For example, let's look at 3 in this function. You can see that the function value at 3 is 1. And the limit as we approach 3 from the left and from the right is 1 as well. The function is trying to be 1 when x equals 3, and the function is 1 when x is equal to 3. In most cases, the actual function value is the limit. It's only when we have some anomalous feature in the graph that we find that possibly the function value and the limit might be two different numbers. Speaking of anomalous features, there are functions that fail to have limits at various points in their domains. If, at a certain point, the function does not approach the same number, or any number at all, from both the left and the right, then the limit fails to exist at that point. Remember the functions we were looking at previously. We saw that from the left and from the right of the function, we could tell from the behavior of the graph what the graph wanted to be at a certain target value, even if the function wasn't defined there. That meant that the behavior of the graph indicated what needed to happen, even if the function value didn't give us information about what needed to happen. Well, if this scenario doesn't occur, we will not be able to find a limit at certain points. Look at this first example, behavior that differs from the right and the left. In this function, we're wondering what the limit would be at x equals 0. As we approach 0 from the left, the function is -1. As we approach 0 from the right, the function is +1. So from the left, the function is trying to be -1. From the right of 0, it's trying to be +1. Because the behavior of the function isn't indicating the same number at 0, then a limit fails to exist at 0 in this function. In this scenario, we have unbounded behavior, where the behavior of the function isn't approaching any number because it's going to infinity. This happens when you have asymptotes in a function. So at 0, from the left, we see that the function is going to positive infinity. It's not going to a particular number. Therefore, it's not indicating a limit. Of course, from the right, it's also going to positive infinity. Because the behavior is unbounded on either side of the target value 0, the limit fails to exist here as well. In this last example, we have what's known as oscillating behavior. There are certain functions which begin to oscillate infinitely many times as you approach a target value. In this case, that value is 0. From the left and the right, as you get closer and closer to 0, this function continues to oscillate wildly between 1 and -1, and there's never a point at which, from the left and the right, you have the same value being indicated. So in this function as well, at 0, no limit exists. Now let's put our knowledge to the test, determining function values and limits of this function. We'll start with letter A. We're asked to find the function value at -4. Well, at x is equal to -4, you can see, as indicated by this open circle, there is no function value defined here. So we would say, for letter A, the function value at -4 does not exist. Letter B says, what is the limit of the function as x approaches -4 negatively? We haven't seen this notation before, and we'll be discussing it in more detail in a subsequent lecture, but for now I'll just explain that that means as you're approaching -4 from the left negatively. What is the limit of the function? So, as we've seen in previous examples, as we approach our target value -4 from the left, we look to see what the function is doing at that point. You can see that it's trying to be a +2. So we're going to say for letter B, the limit of f of x as we approach -4 negatively is 2. For letter C, they're asking us for the limit as x approaches -4 positively. In other words, we're moving toward our target value -4 from the right, and we're going to look at the function to see what the behavior is there. You can see that it is also trying to be 2. So the limit of f of x as x approaches -4 positively is also 2. Now notice in letter D it says, well, what is the limit of f of x as x approaches -4 in general? Because from the left and from the right, the function is indicating the same value, 2 on both sides, we can say the limit of this function as x approaches -4 is 2. Even though we didn't have a function value there, we do have a limit there. Now let's move to a different target point. Let's look at f of 1. So we're looking for a function value at x is equal to 1, and by this filled in circle you can see it's indicated that the function value at 1 is 4. Now let's look at the limit as x approaches 1 negatively. As we move toward 1 from the left, what is the function indicating the value should be? Well, as we move toward the function value from the left, you can see that it's trying to be 4. So the limit as we approach 1 negatively is 4. Well, what about when we approach 1 positively? That's what the next question says. And you can see that on the right side of 1, the function is trying to be a -2. So the limit of this function as we approach 1 positively, the behavior is indicating here a -2. Therefore, what is the limit of this function as x approaches 1 in general? Well, at 1, since the behavior on the left and the right doesn't indicate the same number, the limit does not exist here. Yes, we had a limit coming from the left, it was 4. From the right, we had -2. But because those were two different numbers, at 1 we would have to say the limit fails to exist. Now let's move to our third and final target point, 6. What is the function value at 6? You can see by this red dot, it's defined to be 2 there. Well then, what is the limit of the function as we approach 6 negatively from the left as we're approaching 6? What is the function value doing? Well, it's clearly wanting to be a 5 there. As we approach 6 positively, what's happening? Again, examining the behavior of the function, it is also trying to be a 5 there. Therefore, what is the limit of 6 in general? Well, since this function is indicating the same value on either side of our target point, then we can say the limit is 5 at x is equal to 6. Now once again notice the function value is something different, but remember the limit is describing the behavior of the function on either side of the target point regardless of what the function value is defined to be. That's the end of today's lecture, boys and girls, and since we're discussing limits today, I thought this verse from the Amplified Version was apropos. I have seen that everything human has its limits and end, no matter how extensive, noble, and excellent. But your commandment is exceedingly broad and extends without limits into eternity. Psalm 119:96. Take a look at this picture and tell me if you know what it is. Of course, I can't hear you as well as I would like to. This is an opal. It's what's inside an opal. Look how beautiful this is. God is able to put this incredible beauty inside a rock, which is a great reminder of what He is able to do in our lives if they are surrendered to Him. God bless you, boys and girls.